I hope you're all having a great evening. I am Mr. Ace. Thank you for joining me for this video. In this video, we're understanding and we'll also learn how to predict the eccentricity of an ellipse. We know what the word eccentricity it means with regards to an ellipse. It's how oval shaped or how oblong an ellipse looks. An ellipse can be relatively circular in appearance. It can mimic more of a circle, or it can be quite oval or oblong, in which case it is an eccentric ellipse. This is less eccentric, that's more eccentric. Each ellipse has a center, and this right here is center, but ellipses also have vertices. We'll call that vertex 1, vertex 2. Here we have a vertex, here we have a vertex. The distance from the center to that vertex is your A dimension, and you know that to be the case. See, that's your A dimension. But there's also within the ellipse always two focal points. We can put a focal point right over here and focal point right here. We'll just call this F and F focal points. And here we have another focal point, here we have another focal point. For ellipses which are more circular or closer to circles in appearance, then the focal point is located closer to the center of that ellipse. And the distance from the center to that focal point is your C dimension. But for ellipses which are quite eccentric, then the focal point is located further away from the center but closer to the vertex. And then this distance over here becomes C. The distance from your center to your focal point is C. In all instances, the definition of eccentricity in terms of a formula is C dimension divided by A dimension. And in terms of values, it has acceptable values less than 1 but larger than 0. Not equal to these, but less than and greater than. If it were equal to 0, then ellipse would be no different than a circle. If it were equal to 1, then you would have something which is so eccentric that you would lose the characteristics of an ellipse. But the ellipse eccentricity falls between this range of values, less than 1, greater than 0. How can you predict the eccentricity of an ellipse or understand it with regards to just appearance or with regards to the formula presentation? Before we answer that question, again notice that as the focal points are brought inwards closer to the center, the C dimension decreases and you have something which is relatively more circular. As the focal points are pushed further away from the center and closer to the vertices, the C dimension increases and you have something which becomes more oval or more oblong. Now let's start doing some predictions over here. Let's look at everything over here with this representation we have. From the center to my vertex, I have a certain A value. I have a focal point over here, which I'm just calling F. From here to here, I have a certain dimension, which is C. We can express everything here with regards to limits, and you'll see exactly everything come into play. Our value here, which is approaching something, is our variable C. This exact value that you see over here, C. If C were to approach the center of that ellipse, and you might as well very easily represent that as a 0, you do have an equation over here or an expression, and that expression is C over A. You know exactly what's going to happen over here. You'll end up seeing 0 over A and it'll become 0. Again, I've told you, you have to look at eccentricity here in terms of this. Less than 1 but greater than 0. And this right here is exactly our eccentricity. Of course, we're violating this range over here because now we're actually making something equal to 0, but it cannot be equal to 0. But we can view it as something approaching 0. This limit here very clearly tells you that as the C, the dimension, the distance from your center to your focal point decreases, your entire eccentricity approaches 0 and you become more circular. You'll start looking more of a circle and less of an ellipse. Likewise, consider this limit as C were to approach A, which means now your distance from the center to the focal point is increasing. The distance is becoming more and more close to the distance of that vertex from that center. In this specific instance, C over A, which is your eccentricity, will become more and more similar to A over A, which is 1, in which case you'll start approaching that value. Of course, you can never become that value, but you can approach that value, in which you'll become very eccentric. And you'll start perhaps approaching something like a straight line eccentric. Anyhow, this right here is just an ideal situation. It's not a practical or a real situation. It's something which could happen, but it won't really happen because it would violate the definition of the ellipse. Now that I've shown you this, consider this. When you're looking at an ellipse and an equation, it doesn't matter if it was horizontally oriented ellipse or if it was a vertically oriented ellipse, in which case the equations are x squared over b squared plus y squared over a squared. The prediction of this eccentricity is very easy if you focus right here on A and B. because you know in all instances the c value comes from c square is equal to a square minus b square. If you're presented two equations or any number of equations, one is horizontally or it could be vertically oriented ellipse, how can you predict what your ellipse eccentricity is without doing any calculations? And I'll tell you, this is how you do it. If these two values are relatively very close to each other, you'll have something of this category right over here, where you'll have something which is very uneccentric or very less eccentric and more circular. If the disparity or the difference between the a and b, or the a square and b square, is very large, or there's such a huge discrepancy, then you'll be looking at something of this nature and you'll have something which is very eccentric, and you'll know that to be the case. Think about it in this way. If c square is always representing the difference between a square and b square, if both a square and b square are very close together, then that difference is very small, then the square root of that difference is very small, and you end up having a very small c value. If you have a very small c value, you'll be looking at a situation like this, because it'll be approaching 0. If the a square and b square in terms of their disparity or their discrepancies are very large, because the a square is such a large number and b square is such a small number, then in that instance you'll have a very large, or you just have a large c value, because the difference here is very large. The square root of that difference is also large, and you'll be looking at something of this situation right here, because here your c value will be large, getting close to a, and you'll have something very eccentric. And I can show you all of this here by means of just visual examples. And you always have to bear in mind you're looking at everything here in this form by means of these two limits, and you're also looking at everything here with this form right here, the way by which you determine the c value, because it's always a difference of a square and b square. Consider this example over here, and we'll be looking here everything in the standard form. X square over 25 plus y square over 4 is equal to 1. You know, just by looking at this, your a square is a 25, or you can say a is 5. Here your b square is a 4, or you can say b is a 2. Look at the disparity between these two, 25 and a 4, or 5 and a 2. These are very large differences between these numbers, and those differences will very well show up in this formula, the c determination, and it'll be a situation such as this. And we can show it to you to be the case. If you were to calculate the c over here, and you don't even have to do it, just by the visual disparity between these two numbers, you know you're looking at a very eccentric ellipse. You can do c square is equal to 5 square minus 2 square, and you'll have here a root 21. Eccentricity is c over a, which is root 21 over 5, and you'll see this value will be very large, and it'll be very close to 1, and you'll see it. Root 21 divided by 5, I'm getting a 0.9165. It's quite close to 1, 0.9165. So it's a very eccentric ellipse just by the visual appearance. Now, as a contrasting example to the one I've just shown you, let's look at the situation where the disparities between these two numbers a and b is very small, because those disparities will translate into a very small c value, and you'll have some situation such as this, where you're approaching 0 in terms of less eccentricity, and it'll be more circular. How about something like this? You have x squared over 9 over 10, and then you have y squared over 1 is equal to 1. You know this value is slightly larger than this, because this is like a 10 over 10, this is a 9 over 10, a vertically directed ellipse. But in this instance, in a square here is 1, b square here is 9 over 10, but a is equal to 1 and b is equal to root 9 over 10. You can do 3 over root 10. But if you're looking at these two numbers a and b, the disparities between this is very small. Therefore, c value will be very small. But we can still calculate c. c here will be equal to a square minus b square. It will be root of 1 minus root of 9 over 10. You can put it all under a common parentheses. We can do that. 1 minus 9 divided by 10 is a 0.1. You root it, you're getting a 0.316. 0.3162. I'm saving this value. The eccentricity here will be c divided by a, which will be this 0.3162 divided by a1. And you know the eccentricity here is 0.3162, which is relatively small. The disparities have to be quite small or quite minimal to get very close to 0. And that's how it would work. But generally, in appearance over here, using the appearance, when you're looking at a formula for the ellipse, if you see a very small difference between these two numbers, then you're looking at something which is less oval and more circular. If you're seeing a relatively large difference between these two numbers, a great disparity will arise and the c value will be large. Your eccentricity will be large because your focal point will be closer to the vertices, and you'll have something which is more eccentric, that is more oval shaped. And that's about all I want to say in this video. Thank you for watching. Have a nice day.